Assalamualaikum and good afternoon to everyone. We, great, we, great, we greatly appreciate all for joining us in KPPIM International Webinar 2030 on Mathematical Science Section 10. Hashtag boost our visionability. Your presence is our happiness. My name is Nur Idina Bakis binti Azlan and I am the moderator for today. Before we start, let's visit Surah Al-Fatihah. Alhamdulillah, praise and thanks to Allah. We, back, we are back together in the 10th section. Without further ado, please allow me to welcome Dr. Amirah Mohamad Sahar as the first speaker for our 10th section. Dr. Amirah has served as a senior lecturer at the Universiti Teknologi Mara UiTM Shah Alam since 2022. Dr. Amirah received her PhD in Mechanical Engineering from Brunel University, London, United Kingdom in 2020. Her Master of Science in Mathematics Engineering in 2011 and her Bachelor of Science in Mathematics in 2009 from Universiti Teknologi Malaysia, Sudan. Her, her areas of interest in computational fluid dynamics, fluid mechanics, and heat transfer and applied mathematics. Welcome Dr. Amirah, who will speak for 30 minutes on her research topic, fluid flow and heat transfer in microchannel device for cooling application. A 3D computational fluid dynamic simulation, followed by a 10-minute question and answer session. Give our first speaker a hearty round of applause by clicking the clap emoji. Dr. Amirah, you can.
Assalamualaikum warahmatullahi wabarakatuh. Thank you so much, our moderator for today. Okay, so I would like to share my screen of my presentation for today. Okay, so hopefully all of you can see my screen right now.
Yes, Doctor.
Okay, so I should start. Okay, so first of all, Assalamualaikum warahmatullahi wabarakatuh, and thank you for all participants coming for this evening session for international webinar. Okay, so for today, I would like to present a part of my project, which is entitled of Fluid Flow and Heat Transfer in Microchannel Devices for Cooling Application. So which is this, I will share for the 3D computational fluid dynamic simulation. Okay. Okay, so first of all, I would like to give a brief introduction about the CFD, which is a computational fluid dynamics. So basically, CFD is the process of the mathematically predicting the physical fluid flow, which is by solving the governing equation by using computational power. Okay, so basically, the idea here, when an engineer which is have a task with designing a new product, what they need to do traditionally, the only way for the old engineers is to optimize or the design is to conduct with the physical test, which is experiment setup on the product prototype. Okay, so nowadays, however, by the rise of the computers and ever-growing computational powers, so the field of CFD has become a commonly applied for predicting the real world physics. Okay, so as you can see here, so by using the CFD, the application, yes?
Can you open your camera?
Oh, I didn't, sorry.
Okay.
Wait. How to open it? I should stop first, right? Yes, stop. Okay. Sorry. Okay, so we shall continue now. Okay. So everybody can see me now? Sorry about that. Okay, so basically the application of the safety here, so we can see which is with the fluid flow, regarding with the heat transfer, mass transfer, reactive flow, and etc. Right? Okay, so for the next slide, okay, so basically, CFD is interdisciplinary topic. So here in CFD, what we have a numerical analysis combining with the fluid mechanics and also with the computer sciences. So what we need to predict the flow is a mathematical modeling, which is the partial differential equation of the fluid mechanics. So basically, as if you get familiar with the Navier-Stokes equation, okay. The second one is a numerical method, which is we have a numerical analysis, also discretization, and also the solution techniques. So basically, in CFD, we have finite difference, finite volume elements. Okay, and then the last one is a computer sciences, which is in computer sciences field, we have a software tools and also the solver, pre and also the post processing utilities. Okay, so here is some example of the software tools that are that's normally used to solve or to solve the physical phenomena, which is ANSYS, Fluence, Console, and also the open form. Okay. Okay, so here I would like to show you how does this CFD work actually. Okay, so basically, we start with the pre-processor, which is in this pre-processor, if we have any problem in a real world, what we need to do, we have to create the geometry, which is we call it a computational domain, and then after that, we generate the mesh, which is we need to solve the computational modeling, and then the next step is the solver or the black box. Okay, so for the solver, so normally we have the physics setting, and then we should to select the solver to solve the problem, and then to identify whether the problem is in a laminar or in a viscous model, and then we have to specify the boundary condition for the model, and then after that, for the solution part, so what we need is we have to select the computational algorithm, and then we have to specify the discretization method, and then the next step, which is we have to set the convergence monitoring criteria. Okay, so here all the mathematical modeling will solve in this solver by using this solver, which means all the model that we need to use to solve or to predict the fluid flow, we solve in this step. Okay, and we have to make sure that our solution will converge. If will converge, and the next step, we go to the post-processing, which is we need to check or validate our result in order to make sure that our model is okay and is valid to use to simulate the fluid flow or the heat transfer itself. Okay, if not, what we have to do, if our solution is not converged, what we need to do, we have to go back to the preprocessor, which is we have to create our geometry. So normally we are having some difficulties to generate the mesh in order to get the accurate prediction of the fluid flow. This is the most challenging step, which is generate the mesh. Okay, so for the next slide. Okay, so this is the advantages why we need to use a CFD. Okay, so basically, in a traditional way, what we need to do for the designer, they have to conduct or do the experimental setup. However, by using CFD, we can reduce the cost in order to set up the experiment. So, this is the quick way to assess a lot of the variation of the design. Okay, all right. And the second advantage, which is by using the CFD, we have the comprehensive information, because when you do the experimental setup, they have some limitation in order to get the data. All right. Okay, and then this will enable the designer to simulate with different condition for easily by using CFD. Okay, so here is the motivation of my research. So basically, this is because we have found that a lot of discrepancies in and also the limitation in order to understand the fluid flow phenomena in a literature review. So this is because of due to the measurement of the uncertainties normally happen in experimental, and when they do the the CFD analysis, most of the study is just limited with the one single cell, which is in my study I have multiple channel and also single channel, and then also this led to the over predicted of the heat transfer for performance and also inconsistencies results. Okay, this is because of by using the experimental study, it's very difficult to extract the localized flow and also the temperature data that we need to characterize the fluid flow and also the heat transfer. All right. Okay. Another thing is in for the two-phase flow study in microchannel. So most of the study we conduct in two-dimensional asymmetric. Okay. So with this one will lead to the identical bubble structure. And however, the assumption of the identical generation in the microchannel is not acceptable. And also, we found that the real dry out condition in numerical simulation is still needed. Okay, so here there's some brief introduction of the microchannel. Okay, so basically the microchannel is a concept of the heat removal by the means of the liquid flow in the microchannel. As you can see here, the microchannel devices, okay, which is introduced by the Tukeyman and Pease for the early 80s for electronic cooling. So these devices are demonstrate the heat removal rate about 0.79 kilowatt per centimeter with a single phase flow only. Okay, so the definition of the microchannel is we have a different of the definition here, which is we found and or commonly used is from the handles here. This is the hydraulic diameter. Hydraulic diameter is like is similar with the diameter of the channel itself. Is between 1 to 100 micrometer, and then for the Karnika is 2002 is the range of the hydraulic diameter is between 10 to 200 micrometer. Okay, so basically this definition is depends on the application of the microchannel. That's why we have two various of definition of the microchannel. Okay, so this is my first project by using by using CFD. Okay, so here is the experimental setup which is conducted by Brunel University group, which is they need to do the simulation. They need to predict the fluid flow and also heat transfer of these cooling devices. Okay, so in my project, what I have to do, I have to simulate this experimental setup in order to predict the fluid flow and heat transfer in these cooling devices. So this in this project, I do 2-dimensional, 3D-dimensional computational domain. However, I will present you only for the 3-dimensional computational model. Okay, so if you can see here, this is a velocity inlet, which is this is where our water will flow from the top, from here, and go down and go inside the channel. So this is where the heat source will happen, which is this heat source, this water flow in this channel will absorb the heat from this heat source. Okay, so we simulate these devices. Okay, so what interesting by using CFD actually is we can see the velocity vectors or the velocity profile inside the channel, which is this is not possible to get this kind of fluid flow in a real life. So from here, what we can see, the discrepancies that we found in literature review because of this effect, which is the effect of the entrance line. We found that most of the study assume that the fluid is uniformly distributed inside the inlet of the channel. However, we found the vena contracta effect, which is produced by the sharp edges here at the microchannel inlet. Okay, as you can also see that the velocity profile at the inlet of the channel is not uniformly distributed along this channel. Okay, so another effect that we simulate, that we found in this study, by using this study, is we also consider the effect of the conjugate heat, which is, as you can see before, we only have the thin wall. This is where our fluid or liquid is come in and come out. However, this one we take into a part also with the copper blocks. Okay, so here is the heat source, which is similar, or we call the cartridge heater, which is you can see from here. Okay, so what we found by using this full conjugate, by take into account the conjugate effect, what we found here? We found that the heat transfer rate by using the full conjugate effect, by take into account the copper block, is about 50% reduced from the first computational domain. Okay, so just to bear in mind in your for your information, for the 3D thin wall, we do exactly similar like the experimental data reduction. So we can see that the validation with the experimental data is in agreement. However, if we take into account the conjugate effect here, the heat transfer is much lesser. This is the reason why we found that some discrepancies between in our literature review. So for the next, okay, the reason of why by considering the conjugate effect, because of what we found by using the CFD, we get that the heat flux, which is at the top, at the side and the bottom of the channel, is not uniformly distributed along the channel. Okay, so you can see clearly here. Okay, so I do the comparison between these 4 different model here. So for the 2D dimensional and also for the 3D thin wall. So which is I consider also only one-sided heated and three-sided heated. So this assumption exactly like experiment. So you can see that the heat flux which is assumed is uniformly distributed from the inlet to the outlet of the channel. However, if we take the consideration of the effect of the conjugate heat, so we can see that it's likely decreasing along the channel. This contribute with the reduction of the heat transfer or the Nusselt value. Okay, this is another effect that are investigate by using the CFD analysis for the previous computational domain, okay, which is I check the effect of the aspect ratio. So the aspect ratio is the ratio between of the height of the channel, because I'm using the rectangular channel. So the height of the channel divided. Is there any question? No. Okay. So with the ratio of the height and the width of the channel. Okay, so basically what we found, we compare our result of the friction factor with the existing existing model from Singh et al. Okay, so we see that excellent agreement of the thin wall model that we use with the experimental data arise from the assumption of the uniform constant heat flux. Okay, so okay, so we can see that there's no effect of the aspect ratio, which is we can see for the Reynolds number for the 500 of the Reynolds number, we can see that the profile is nearly the same. This is the reason why we cannot see any effect in the friction factor, which is contribute for the pressure drop. Similar with for the highest Reynolds number, which is about 1,500. We can see there's a lot. The effect of the very slippery profile is not clearly see from this graph. Okay, so the advantages of using CFD, we also can show the velocity profile in a localized place. Okay, so we can see how the velocity and also the temperature development from the inlet to the outlet of the channel. Okay, so this is my second project. Okay, so previously I have a single channel, which is the micro devices, the cooling devices only have one channel. However, this is the application for a multi-channel cooling device. Okay, so the problem in a micro channel devices is the performance is effect when the flow distribution inside of each channel is not uniformly distributed. So this will affect the thermal performance of this cooling device for the multi-channel. So by using the advantages of the CFD analysis, okay, so we found that the flow is not uniformly distributed at the edge of the microchannel here. Okay, so we found that the separation, they have a separation flow happen at the sharp edges of the microchannel devices. So we propose for a new inlet manifold design, which is by reducing the sharp edges with the corner edges here. Okay, so what we found said we can reduce the vortices happen or vortices phenomena at the edge of the microchannel, and then in order to see the effect of the vortices happen at the edge of the microchannel, so we compare the maldistribution vector. So maldistribution vector actually is a number to see the velocity is uniformly distributed. So the less here, the less maldistribution number is denote with most uniformly distributed of the flow. Okay, so we found that the distribution factor value reduced by about 50% compared to the original design. Okay, so we can see the effect of the non-uniform flow affect the thermal performance of the multi-microchannel devices. Okay, so here in previously I show you two project for single phase flow. So here we have the result that I get from CFT analysis for two phase flow. Okay, so as here this one is the visualization data from the experimental setup, and then here is a 2D asymmetric model, and here is the result of the two phase flow by using a 3-dimensional model. Okay, so as you can see here, by using the same operation condition that set in the experimental data, so this two model, which is 2D and the 3D, is in agreement with the experimental result. However, you can see that by using the 2-dimensional model, the shape of the bubble inside the channel is identical along the channel. However, this assumption is not acceptable. This is because you can see there are various shape of the bubble inside the microchannel from the real data, and this is what we can show by using the 3D dimensional data. Okay. Okay, so because of we found that there's a non-identical shape of the gas bubble inside the microchannel, so we have to analyze the velocity and also the temperature profile of the gas slug and also the fluid inside the channel. Okay, and also we found that by using our simulation, we can see there's a dry zone happen inside the channel and also the irregular shape of the slug flow. Okay, so here, the advantage by using the CFD, what we get is we can extract or get the velocity profile at the certain place that we need to analyze. Okay, so here is the velocity profile of this gas bubble. Okay, and then here is the temperature profile of the gas bubble. So you can see that for at the tails of the bubble here, which is Y2, okay, so you cannot we see that the velocity profile is not in a parabolic shape. All right, so for this will give a difference profile for the temperature profile for the gas bubble. Okay, so the most important thing in this study is first, we managed to get the dry out region, which is we believe that when we do the analysis by taking the temperature along the channel for the wall temperature, which is here is the wall of the temperature, and also the fluid temperature in here, you can see there's a various temperature data, okay, and then for the bubble slug, we're having the dry out region have very high wall temperature, and this contribute to Okay, so the dry out region contribute to the lower Nusselt number. Okay, so which means that if we have the dry up inside the channel, this will reduce the performance of the cooling device itself. All right. So by using analysis of the CFD, we can manage to get the data of the nussels or the heat transfer from the inlet to the outlet of the channel. Okay, so here there are some the research contribution. First is we found that the 3D full conjugate simulation can help in determine how much is the error due to the assumption of the uniform heat flux, which is mostly used in the experimental data reduction. And then for the geometry examined that in the present study, this error was found to be more than the 50% on the average. And then the second thing for the multi-channel cooling device, so we propose a new design which is with the smooth edges, which is this one we believe that can reduce the occurrence of the flow recirculation and also improve the flow distribution and also the thermal performance of the devices. And the last one, we can say that the non-identical shape of the gas bubble slug was observed by using the three-dimensional computational domain, which is we found that there are the dry zone and also the irregular shape obtained, and which lead to the variation of the wall temperature behavior and also effect on the heat transfer rate. This is because in experimental, they assume that the temperature for all of the along the channel is similar. So we showed that this assumption is not realistic. Okay, so for the conclusion, so the conjugate simulation is need to be carried out to accurately predict the microchannel heat transfer rate. And then a newly design of the inlet manifold is proposed, which is the sharp edges at the inlet manifold were smooth to reduce the occurrence of the flow recirculation. And the third one, the study showed that CFD can be used to obtain a realistic of the two phase flow pattern maps, and also the dry out that occur at the tails of the bubble slug is minimized the heat transfer rate, which is contribute to the reduce to the thermal performance of the devices. Okay, so here is the some recommendation. So I will for the further study, I will plan to get a mathematical modeling of the two-phase flow for the Taylor flow, which is the slug flow that I showed to you previously, which is this is for the combining of the two different fluid, which is a non-Newtonian and also Newtonian fluid in a microchannel. Okay, so this is basis on the general conservation, which is when we have a momentum and continuity equation with the correlation of the film thickness. Okay, so here's some of the resource page that you can see if you are interested to join with me to do the research. Okay, so thank you so much. If you have any question, you can ask me. Thank you.
Thank you, Dr.
You're
Amirah.
welcome.
Now we will open our question and ask session. Please feel, please feel free to leave a comment below or speak up directly.
Okay, Dr. Amirah, I have one question.
Okay.
What are the key advantages of using microchannel devices for cooling applications, particularly in comparison to conventional cooling methods?
What the advantages? Okay.
Using
so-
microchannel devices.
Okay, so by using the microchannel, what the advantages compared to the conventional? For the conventional is more, the hydraulic method is more than 1 millimeter. The advantages is this is a compact devices. It's very small, and then it will reduce the cost in order to develop the devices. And also the most important thing for the microchannel, give the most ini. Sorry. Is it okay? Dr. Rini, is that okay?
Okay, clear.
Okay, thank you.
Okay, and one more question.
Okay.
How does the geometry and size of microchannel affect the fluid flow and heat transfer in these devices?
Again, how does?
How does the geometry and size of microchannel affect the fluid flow and heat transfer in these devices?
How the microchannel affect the fluid flow and heat transfer in microchannel?
Yes.
Okay. Okay, so basically, if you can see previously, most of our computer is much more bigger, right? Much more bigger. Our phone also much more bigger compared to now. Okay, so how to emphasize? Okay, so basically, for the microchannel, really, really,
Yes?
sorry. Gosh. Hello, can you hear me?
I think your internet is lagging.
Sorry. I think,
So
okay,
you need to
sorry.
repeat again the answer.
Can you repeat the answer again? Sorry, I almost forgot about that.
Uh, how does the geometry and size of microchannel affect the fluid flow and heat transfer in
Okay.
these devices?
Okay, thank you so much. So basically, the microchannel, compared to the conventional, it will give you a different phenomena of the fluid flow. Okay, which is for the microchannel, the fluid flow is more complex compared to the conventional one. However, because of the microchannel, give you a most high heat transfer rate compared the heat transfer. So that's why we need to emphasize the microchannel emphasize the microchannel compared to the conventional. Is it okay, Dr. Rini?
Okay. Clear.
Clear.
Thank you.
You're welcome. Any other question? Any other question?
Anyone
the chat.
else want to ask a question? Anyone else? I think it's no one. Okay, thank you, Dr. Amirah, for
Okay, welcome.
your sharing. Okay, let's go on to our second speaker, Dr. Zuraidi Saad. Dr. Zuraidi Saad obtained his undergraduate degree from the University of Applied Science and Business early in Germany, specializing in micro and precision in precision engineering. Microtronics is an SC degree from the School of Electrical and Electronic Engineering USM, specialized in electronic system design, engineering, and finally, he gained his PhD in Mechatronics Engineering from Faculty of Electric Engineering Technology, UNIMED. He developed, he developed his career by joining the Department of System Engineering, School of Electrical Engineering, UITM, as a senior lecturer in 2013. He has published several scientific articles in some index journals and has a wide range of international collaborations. His research interests including online modeling, forecasting, classification, artificial intelligence using neural networks, image processing, control system, and automation using pneumatics. We would like to formally welcome Dr. Zuraidi, who will give a talk entitled Trusted and Balance of Fuel Forecasting Using Trends Data Hybrid Multi-Layer Synchronous Network for 30 minutes followed by a 10-minute question and answer session. Please click a clap emoji to give our second speaker a hearty round of applause.
Okay, thank you, Miss Moderator, Miss Idina Bakis, and Dr. Rini, and all participants for KPPIM International Webinar 2023 on Mathematical Sciences. So I'm Zuraidi Saad from Electrical
Dr. Zuraidi
Engineering
Saad.
Studies.
Can you
Okay.
open your camera?
Okay. Is my camera functioning well?
Yes.
It's okay.
Yes, doctor. I can see you now.
Hmm?
I can see you now.
My camera is okay. Oh, no, okay. Okay. So, sorry. Kerja out. Open door. Okay, again. So my name is Dr. Zuraidi from Electrical Engineering Studies, UITM Cawangan, Pulau, Pinang. So today I'm going to present my webinar entitled Cost, Speed, and Balance of Field Forecasting System using Hybrid Multi-Layered Perceptron Network. So my presentation consists of introduction, problem statement, research objective, the scope of the research, methodology, result and discussion, and last but not least, the conclusion. So cost, speed, and balance of field forecasting system, both model,
Like,
yeah, like not run. So I think I cannot use the. I cannot use. Okay, now it's okay. If I don't activate the slideshow, can you see it clearly?
so, can you say your slide? If can't, we share your slide.
I didn't hear you.
Sorry, Doctor?
Or I didn't share the slide. Okay.
Okay, Doctor, you can see now.
It's okay. Oh, that's it. Okay.
Okay, Doctor, you can see now.
Okay, I continue. So cost, speed, and balance of field forecasting system, both model mathematically have a good relationship. So both are important model in the future of automotive industries because it can be applied for eco driving, engine performance, and engine diagnosis. So for hybrid multi-layer perceptron, basically, previously it was applied as an early flood water forecasting and carbon monoxide concentration of forecasting. And recently it was popular as a disease diagnosis and applied as a satellite controller and other application. So problem statement, overseas such as Japan and German thought were model and test at their environments, where the road quality, different maximum curve, and gradient of road and temperature are totally different. For example, car model in Japan will be accurate at Japan and not tested at other country. So I want to model an online car model which can be accurate at any country. So most of the present model car were using an offline model where the output data is predetermined or pre-calculated. Therefore, the warning or alert signal are depend on static data, which is not real. So many passenger car drivers who have experience while using auto cruise mode by climbing a hill, a car suddenly slow down, or while downhill, the car engine suddenly drive. So this phenomenon indicates that a model that has been built offline using an industry standard practice to cut fuel during coasting and refuel at low engine speed fail to accurately predict car speed. So my research objective, the first one is to improve the architecture of SMLP network by including an additional input function for online training data. Secondly is to formulate a new hybrid learning algorithm for the new HMLP network. And the last one is to develop online modeling and forecasting technique for car speed and balance of fuel in tank of the car. So the scope of research. So the target user of the system is only for a compact car, class C only. So may not suitable for other class of car, but it should adapt because online modeling will learn continuously. So the plus highway and most of federal highway are the projected road for the research, specifically from Sabang Jaya roundabout to exit to Jawi back to Sabang Jaya roundabout. So the model are not tested for a road with highly and curvy trails such as Karak Highway and Timur Barat Federal Highway. So may not offer the same accuracy, but it should adapt because online modeling learn continuously. So the finding from my literature review, I found the most of previous researcher applied the online training. For example, Huang et al. 2015, one of the researchers applied online modeling and mentioned that online modeling can improve the prediction of instantaneous fuel consumption without calibration. And then Sean et al. 2019 applied online training to forecast an average fuel consumption where the result of R square is only 0.91. So if they apply online modeling, this R square will be more accurate. So in my experiment, I can get 0.98 to 0.99 for the R square result. So tendency, most researchers apply the offline modeling as I mentioned in previous slide. So moreover, the only model, the fuel consumption result, a modeling of the speed. So in my research, I model the speed and balance of fuel or fuel consumption at the same time. So both speed and balance of fuel have a very important relationship in the advancement of automotive. So this is the search for modeling and forecasting through Google Scholar. So most of them apply online modeling and forecasting. So this is the search in the range of 2016 until 2021. So only two of them apply online modeling and forecasting. In fact, two of them are from my publication. So for methodology, so I did this research using the HMLP network. Other networks such as MLP, RDF, recurring can be used as well, but these networks are heavy and slow. So HMLP can be converted quickly by simply using a lower hidden nodes and lower epoch. So Masho has successfully done a project like this using HMLP network, but for other applications. So I plan to improve the HMLP network and learning algorithm that he used, which is MRTE. So this the trend data HMLP that I have proposed for online modeling and forecasting. The innovation I made is in the red circle. This red circle at input layer I. This is input layer I. It is the input function work to automatically the trend data in the online manner. So the conventional HMLP network only have the activation function at the hidden layer J. So the standard MLP that commonly found in the MATLAB software just have only the straight line. So the dotted line is innovated by Masco 2000. So in the HMLP network, I just propose the additional input function that meant for to remove the DC effect in the online data. So this is the equation for HMLP. So after I add on the additional input function, so we have the additional GI function. This is the GI function. Previously, there is only WIK times VI. So we have to put the GI function at this portion and also at this second portion of the algorithm. So from the TD assembly input output function, so this is the TD assembly input output function that I have proposed. So the GI function have to be selected for different type of design method. For this project, I select two types of design method, namely as FDD, that is first differential difference, and the second one is DHPF, stand for digital high pass filter. So this is the equation governed to FDD, and this one is the equation for DHPF. So other method that can retain the input in online manner also can be applied. So after the modeling and forecasting is done for every cycle, the transformation to original data or trend data is performed using this equation, these two equations. At the beginning, we have to remove the DC effect from the online data, and after we model, we have to return back to original. So why I have removed the DC effect using the input function, because if we model, in my experience, if we model using the data with DC effect, so the model are going to be a bias. I'm going to show you later with the in the result how the bias effect in our online modeling. So more or less about the history of RPE or recursive prediction error that I have modified to be ALRPE. So originally, the RPE is derived by Lang and Soderstrom in 1983, and then it was modified by Chen et al. In 1990 to train MLP network. So Chen modified RPE using a constant value of momentum and learning rate, and after that, Maso 2000 start to use a very value of momentum and learning rate to train HMLP. So in 2015, me and Maso and Wan Kabnurizam have proposed the ALRPE for the advancement of this kind of learning algorithm. So I have published the new algorithm in formation of momentum and learning rate profile for online training and testing of HMLP with ALRPE. So this is the original MRPE. Learning equation to update the momentum rate and learning rate. So at this point and until now, I am the one who classified and published in my thesis the MRPE into two types of version 1 and version 2 based on my study with my supervisor and through his previous project for my proposed ALRP, I also proposed two versions of learning algorithm, namely as AL1 RPE and AL2 RPE. So this is the original algorithm. So this is the momentum, and this is second one, the learning rate for M1 RPE, and this is the learning rate for M2 RPE. So these two versions of MRPE has its own application. So my hypothesis to improve MRPE using the proposed MRPE, I have slowed down the momentum and learning rate of MRPE using the new algorithm that I have named as an adaptive learning RPE. So in my AL1 RPE training algorithm, so to update the momentum rate and learning rate at every learning cycle in AL1 RPE, so alpha M and alpha G alternately update based on equation A and equation B. And for the second proposed AL2 RPE training algorithm, same technique goes to AL2 RPE, alpha M and alpha G is alternately update based on equation A and equation B. So this is some of momentum and learning rate profile. So previously MRPE was developed only on the basis of its general algorithm. So today I will present and highlight a more detailed study on formation of learning and momentum rate profile and how to improve that. So the technique is simple. Firstly, I set the alpha M and alpha G as initial value, and then run the online modeling and plot them and analyze the forecasting performance using such as online MSC and squad. So it is more interesting and enjoying tuning with both number and picture instead of a blind tuning. So this figure 2 is the example of plotting formation of alpha M and alpha G during online modeling and forecasting using heat exchanger data. So using my proposed ALRPE technique, both AL1 and AL2 RPE is easy to improve to be improved in terms of performance of ALRPE and MRPE by modify the profile to make it learn with more or less number of data. So forget about the momentum and learning rate. Now we go to the modeling nonlinear system. So for modeling nonlinear system to forecast speed and balance of fuel and others support experiment, I choose the NAMEC model. To select the input output and noise vector lag, I use the growing technique instead of pruning technique because for my experience, it is more practical and time consuming for most HMLP type network. So this study used Proton Gen 2 with an automatic 1.6 liter temper engine which produced 110 maximum horsepower at 6,000 RPM and 148 Newton meter of maximum torque at 4,000 RPM as the target vehicle. So figure 2 is online data monitoring system that I have developed with my team, and figure 2B is a rear view of external single board computer that used to download the online data. So figure 3 is the flow chart of my methodology in detail. Is so fine. So better I explain in terms of experiment block diagram. So from the previous block diagram, I want to explain the flow of my work using this experiment block diagram. I divide my work into 4 types of data where my main data is speed and balance of fuel. The rest, electrical power and heat exchanger, is my benchmark data to support or validate my proposed PDHMLP and is performance that I have proposed. So the result of this benchmark data, these two is the benchmark data, is evaluated using correlation test, MSE, and one step ahead forecasting. For the speed and balance of fuel, I have done extra evaluation using multi-step ahead forecasting, or MSA, where MSA is a measure using R square for speed and balance of fuel. So this is some result. Simulation result have shown that the proposed LRP momentum and rate profile will improve the efficiency of the nonlinear HMLP MRP model in the one-step ahead forecasting model, validity in the range of 0.42 dB to 1.33 dB for MSC, and R square is improved from 0.008 to 0.0015. So the result of the forecasting indicate that TDHMLP 2 RPE network is better than TDHMLP and 2 RPE network in order to sustain R2 greater than 0.8. So to produce better result for the correlation test and to generate 2 better steps for speed forecasting in MSA. So the result indicate that TDHMLP AL1 RPE network is better than TDHMLP M2 RPE network in order to sustain R square higher than 0.8. So to give better result for the correlation test and to produce one better multi-step for better of fuel forecasting. So in the journey of my research to validate my previous final result, I have conducted several experiments. So the result in the introduction, so I have shown the impact of trend data to the performance of speed and balance of fuel forecasting. The result show that the trend data will produce major error in correlation test. In experiment 4.3 is the comparison of HMLP and TDHMLP network using EP data that consists of highly trained data. So the result show that the use of TDHMLP has a small improvement in terms of a model tend to be biased, and the model has surpassed almost all correlation tests. So in experiment 4.4, there is a comparison of HMLP and TDHMLP network using heat exchanger data, which are already different data. The result show that the TDHMLP network tend to cause one step ahead forecasting, R square and multi-step ahead, and MSC and correlation test to be slightly deviated, but still in acceptable range for forecasting performance. For in the last experiment, there is experiment forecasting system using TDHMLP after experience the advantage of TDHMLP. So at this stage, I compare the performance of 2 types of my proposed PE with the performance of 2 types of conventional mRPE. Okay. Okay. Three types of data were modeled using this NAMA model. I select M2RPE to compare the effect of trend data. So the design parameter is set as follow for original data or trend data, FDD and DHPF. So from the highlighted part in the one step ahead forecasting in figure 4.1, this one, it shows that the original data affected the lagging effect in the Shah. So however, this lagging effect has been trimmed down with the trend data using FDD in figure 4.2. So this trend data using digital hyperfilter in 4.3 has been slightly improved to perform a better result. This minimum lagging effect and fast spot of forecasting. So this is a result of forecast using two balance. The same effect can be clearly seen using phase differential and digital hyperfilter. So this is the result for R-square test. So we can see the FDD and digital hyperfilter has improved the R-square for both experiments for speed and the length of field. So this is the major effect that I have explained before. In original data, if the data have the DC effect, so it fails in the correlation test. So but for both FDD and digital hyperfilter, so this effect has been avoided. Same goes to true balance data. So this major error from correlation test sometimes cannot be differentiated from our naked eyes. If we use the one step ahead forecasting, result only to validate the forecasting performance. That's why I have conduct also the correlation test. So correlation test actually the tough test that has to be passed for online modeling and forecasting. So for electrical power data that were modeled using this model, I select M1 RPE to compare the effect of highly trained data using my first benchmark data. So the design parameter is set as follow for both HMLP and PD HMLP model. So some improvement can be seen in the residual for the model using PD HMLP. So we can see clearly the residual is in between -10 and 10 after using PD HMLP compared to HMLP M1 RPE. So the residual is in between -20 and 20. So some improvement also can be seen in the R-square and MSC during during testing for the model using a TD-HMLP. So the green one has learned more faster to be and achieve the lowest MSE after only 200 data, and achieve the lowest MSE after 700 training of data. So correction test for ET data. So this major error again prove that the model that have highly trained data using benchmark data 1 will affect the model to be biased. So we can see round circle with in purple are the error that found in correction test using HMLP M1 RPE, but this error is improved using TD-HMLP MRPE. So for heat exchanger experiment, heat exchanger data were model using this NAMAD model. I select M1 RPE to compare the effect of the trained data using my second benchmark data to the TD-HMLP network. So the design parameter is set as follow for both HMLP and TD-HMLP model. So the result, the results can be shown in figure 4.20 and table 4.5. So from this comparison, some degradation can be seen in the R square and MSC during testing for the model using TD-HMLP. So for the correction test, some degradation also can be seen in the correction test for the model using TD-HMLP, but still in an acceptable range for forecasting performance. So for experiment using LRPEs in the external forecasting using TD-HMLP network, split over model using this NABA model. So this is the comparison of ALRPEs and MRPEs learning algorithm. So the result is here. So this is the formation of AL1 RPE learning algorithm profile and formation of AL2 RPE learning algorithm profile using split data. And this is the conventional of M1 RPE learning algorithm profile and M2 RPE learning algorithm profile. This is the conventional algorithm. So the result of MSE comparison using speed data using TD-HMLP. So the results show that AL1 RPE in the blue, in the dark blue, can converge very fast within 60 data and finally achieve 23 dB. And finally give the best minimum MSE among the learning algorithm comparison. So the second runner-up is 2 RPE, third runner-up is M1 RPE, and the last one is M2 RPE in the light blue. So my proposed algorithm is on the top, the dark blue and the green one. So this is the best, one step ahead forecasting for speed using TD-HMIP AL1 RTE network. So this is the best correlation test for speed. So for experiment using balance of field forecasting system, so balance of field were model using this NAMAC model. So this is the comparison of ALRTEs and MRTEs learning algorithm. So the detailed design is for the learning profile is here. So learning profile for MRTEs. And the result of modeling during training and testing, online during training and testing. So the result show that AL2 RTE can converge very fast within 60 data, and it achieves 34 dB, and finally give the best minimum MSE. And the second runner-up is M2 RTE. The runner-up is AR1 RTE, and last one is M1 RTE. So this is the best for one step ahead for balance of field. And this is the best question test for balance of field. And then we go to experiment of heat exchanger forecasting system, the third model for this project. So heat exchanger data were modeled using this NAMAC model. So this is the comparison of ALRTE's performance using second benchmark data versus conventional MRTEs. So this is the learning algorithm profile using AL1 and L2 RTEs. So this is the conventional M1 RTEs and M2 RTEs using the heat exchanger data. So the result shows that AL1 RTE can converge very fast within 50 data. And it achieved final minus 15 dB and finally give the best minimum MSE. And the second runner-up is AL2 RTE. Third runner-up is M1 RTE, the red one. And last one is M2 RTE. So for benchmark data 2, so this is how the heat exchanger data for using for training and or as input, and the output is the second one using for testing, use as a testing data. So the result for one step ahead forecasting, we found that AL2 RTE are the most or the best learning algorithm in this comparison. So this is the best quality test and come from the heat exchanger experiment. And table is comparison learning algorithm using HMRT network. So we found that the proposed LRTE again MRTE, the R square is at par, and for MSE it has improved about 0.5 dB. And for the experiment using multi-step ahead forecasting for speed data. So all models in the study were simulated by the following configuration. So this is the model that I use, and for the design parameter, and I have tuned and get the best parameter for all learning algorithm that has been compared. So the best MSA for speed is found using the PDHMLP AI2 RP network. So this is the R square comparison of MSA for speed forecasting. So the design parameter is here. And then this is the result for multi-step ahead for balance of fuel. So the best come from the model of PDHMLP AI1 RPE network. So this is the R square comparison. And so for the conclusion, PDHMLP ARP network has been modeled with NAMET model and validated. So digital high pass filter design method is selected as the best technique among the comparison to eliminate the cheese effect that can cause major error in the correlation test and forecasting. So the third one, the analysis has been proved by the higher accuracy level of forecasting, which is done by PDHMLP ARP network. So the hypothesis to improve the performance of nonlinear HMLP modeling by slowing down the learning rate and momentum rate using adaptive learning to the MRPE was scientifically agreed by a good performance of ALRPEs in almost all validation process. So for the research contribution, so a TDHMLP was proved to be successful for online cost speed and balance of the fuel forecasting system. The ALRPEs were proved to be successful for online cost speed and balance of the fuel forecasting system using the proposed TDHMLP network. In A, the TDHMLP ALRPE forecasting model were proved to be successful to forecast the cost speed and balance of fuel for Proton Gen 2 car. So new multi-step bucket model using TDHMLP ALRPEs were proposed and proved to be successful to replace TDHMLP MRPE with a more reachable step in multi-step bucket forecasting. So from this research, I have done several publications. So these are from the conference, and two papers were published in journal and one was published in book chapter. So that's all for my presentation. Thank you for your attention. So if I have more time, I can do some demo on how we model online modeling and forecasting. I try. I just want to show or demo the modeling of online model. Can you see the output? Oh, tak boleh kan? Okey. Ah, sekejap, siap. Salah. Kali ini. Salah klik. Boleh nampak? Can you see the output from my simulation?
Tak betul.
Can or cannot?
Cannot.
Tak nampak.
Tak nampak? Tak nampak tak apa. Maybe next time I have to make a video. Okay, that's all for my presentation.
Thank you very much for your sharing, Dr. Zuraidi. Now we will now begin the question and answer section. Feel free to leave a comment below or speak up directly.
Hello, can you hear me? Hello, doctor.
Yeah,
So I have a question. Can we apply the same model or system to roller coaster ride so that we can identify the suitable as well as safety for roller coaster?
I cannot hear you actually. Your voice is echoing. Echo. Can you type at somewhere in this chat? You can type this question using chat. Better for me to answer.
I repeat, can we apply the same model or system to roller coaster ride so that we can identify the suitable as well as safety for roller coaster?
I didn't get you. Please type using chat.
Okay.
Oh, the question is from Saiful Ahmad. Can we apply the same model or system to roller coaster route? Roller coaster. Okay, the same model can be applied to any system. The important in the modeling using neural network, the data must be heavy enough. What is mean by the heavy data? Heavy data also mean that the data is rich enough, ataupun dalam in Malay, data yang kaya. In modeling, the rich data is very important. If we have a rich data, our model cannot be biased. So how do we look, how the rich data look like is, you can see previously in my slide. For example, wait, I share again my presentation. How the rich data look like is as a speed data. Where is the speed data? Data. Okay. Dia nampak kan slide saya? This is EP data. Nampak? How the rich data, this is some of the rich data look like as EP data. So the data has to be fluctuate up and down. Another example is the rich data can be found as this one. So rich data. The rich data in from 0 to 500 data is a rich data. And 500 to 1000 is sometimes normally we use for testing. For training, we must use the very difficult data or rich data. The fluctuate or the frequency is very high, and for testing is more easier. So this is an input and this is the output for heat exchanger data. So in the heat exchanger data, clearly we can see there is the limiter at 500 data. The data has been deleted or split. So where is the split data? This one also rich data. If you examine clearly, so the car has been drive from 0 from the still stand to 60 kilometer per hour, and then it speed again to 100 kilometer per hour, and then the car is brake until it reach the 60 kilometer, and then again speed again to 300 kilometer per hour, and then brake until 60 again. So this is how we collect rich data. So the car that I have used to experimental the process of collecting the rich data has to be driving so fast and brake, driving fast and then brake, and sometimes I have we have reduced the speed from 100 kilometer per hour to be stopped, and then again drive it back. So within 770 data, so this can be a rich data. If you drive the car slower and then you take the unrich data to model your system, so the effect of your model might be biased. That's why we need the rich data like this. Okay.
All right, Doctor. Thank you.
Okay.
Anyone else want to ask a question? Okay. I think that's all the Zuraidi.
Okay, thank you, Mr. Saiful Ahmad.
Thank you so much, Dr. Zuraidi.
Okay, thank you.
Next, let's go on to our photo session. I hope that everyone will turn on their camera for this. Everyone ready? I hope everyone is now prepared. Please look at your camera and give a thumbs up. 1, 2, 3. Smile. Again. 1, 2, 3. Last one. 1, 2, 3. Okay, thank you. Dear participants, kindly Dear participants, kindly fill the attendance form to get your e-certificate and training our purpose for UITM staff. You will receive an e-certificate once you fill in the attendance. We appreciate your presence and also we want to express our gratitude to our speaker, Dr. Amirah and Dr. Zuraidi for sharing their input, sharing their information with will provide the participants with some interest, knowledge. Join us again and be inspired to learn more. Please feel free to contact our speakers via their email for further collaboration. Before we end the session, let me share with you one quote for Aristotle, an experienced mathematician. I don't, I don't have any magical ability. I look at the problem, I play with it, work out the strategy. Until we meet again for our 11th session. Have a great weekend. Assalamualaikum. Bye.